So when you're trying to compare whether two hydrogens are, which of two hydrogens is more acidic, which hydrogen is more likely to come off of a molecule and add to the positive charge in a solution, and you don't have Ka values or pKa values, then there are these four factors we've been discussing that you want to consider. And first you would consider which hydrogen, what the atom was like that the hydrogen was on, and if that tied, you would consider what resonance the hydrogen left behind, and if that tied, you would consider how many electronegative atoms are nearby that could spread the negative charge out through induction. If that ties, though, you go to this last factor, and that is the orbital that the negative charge would be in. So, if the hydrogen is bonded, I should say, if hydrogen is bonded to an sp hybridized carbon, that's most acidic. And if it's bonded to an sp3 hybridized carbon, it is least acidic. And of course, sp2 would be in the middle there. So an sp2 hybridized carbon would be less acidic than sp, but more acidic than sp3. So it's in between. Okay, so that's the rule. The reason behind it is because of the shape of these orbitals. So if you think about an sp orbital, you're mixing an s orbital with a p orbital. Those hybridizations are really recipes for how to make the new Frankenstein orbital. So an sp orbital mixes in one s with one p, and you end up getting an orbital that looks a lot like an s. The s adds to one lobe because it's 50% s. So that's sp. If you compare that to sp2, well, now you're adding the one s to two p's. You're mixing those, and now it's only a third s, whereas before it was half s. And so this starts to look a little bit more like a p orbital. It gets elongated a little bit. And finally, if it's sp3, well, now you're adding the s orbital to 3 p orbitals. So now the s orbital is only 25% of the final orbital, and it looks a lot like a p orbital. So notice, if the hydrogen is bonded to an sp orbital, when it leaves the molecule to act like an acid, it would leave the negative charge with a lone pair behind in these orbitals. Now the nucleus is where the node is. It's where the two little loops sort of meet. Notice that in an sp orbital, the negative charge is kept really close to the nucleus. Because it's 50% s, this is like a sphere. It's not very elongated, and that keeps the charge really close to the negative charge of the electrons really close to the positive charge in the nucleus. And as you go down and you look more at the sp3, look at how far this is keeping the electrons from the positive charge in the nucleus. So because the sp orbital holds the electrons closer to the positive charge in the nucleus, it stabilizes them so that this negative charge is the most stable, and this negative charge would be the least stable, because this negative charge is closest to the positive charge in the nucleus, and this negative charge is furthest from the positive charge in the nucleus. So that's the reason behind it, and this is the rule we're going to use. So you'll recognize these, remember, because an sp carbon, hybridized carbon, usually has 2 pi bonds. You need the other 2 p orbitals to form 2 pi bonds. So you only have the 1 p orbital left to mix. sp2 will only be involved in 1 pi bond. That's what it's using the one extra p orbital for, so it only has 2 left to mix, because you have 3 total. And sp3 hybridized carbons you'll recognize because they'll have 0 pi bonds. They'll all be sigma bonds around them. Okay, so if we apply that to this, on this left side you have ethene, it's a plant hormone, it makes fruit ripen. On the right you have a molecule called acetylene, they burn that in welding torches. And the question says, identify which of the compounds is more acidic and explain your choice. Now anytime you have to decide that qualitatively, you want to go through all 4 factors, ARIO. So first, are any of the hydrogens here on different atoms? No, all of the hydrogens are on carbons. So that's not going to help us. Next, resonance. If any of the hydrogens leave, do they leave any resonance behind? And they don't. All of these hydrogens are on an atom in a double bond, so the lone pair with a negative charge would be on an atom in a double bond. Therefore, it's not allylic. Allylic means you're 1 atom away from an atom in a double bond. And so it's not involved in that resonance pattern, and it's also not involved in the other resonance pattern that has a lone pair, which is a lone pair next to a positive charge. There's no positive charge in the molecule. So that's true for both of these. You get the lone pair here. If this hydrogen left, the electrons in the bond would become a lone pair on that carbon. And so none of those lone pairs are involved in resonance, so resonance doesn't help us. So then we go to the next one, induction. Are there electronegative atoms nearby in either of these molecules? No, we only have hydrogen and carbon. Really electronegative atoms are those ones in the far right, in the top right of the periodic table, things like nitrogen, oxygen, fluorine, chlorine. And last but not least, we come to this orbital. And this is where the molecules differ. This carbon is that carbon has 1 pi bond. That means it's using one of its p orbitals. So it can only mix the 2 other p orbitals together, and it's sp2 hybridized. The carbon, both of the carbons in the other molecule, let's just look at the one on the right, has 2 pi bonds. That means it's using 2 of its p orbitals, so it only has 1 left over, so it's sp hybridized. And what we saw was that sp hybridized carbons, the hydrogen on those is the most acidic. It's more acidic than sp2 hybridized, than a hydrogen on an sp2 hybridized carbons. So this molecule on the right, that's the more acidic one. And if you were trying to visualize the reason why, it's because if the hydrogen leaves, the orbital, this carbon, I'll draw it right underneath, this orbital is an sp orbital. So if the hydrogen leaves, and it leaves the electrons in this bond as a lone pair with a negative charge, it'll leave that lone pair with a negative charge in an orbital that's very much shaped like an s orbital, so it's spherical, and it holds that negative charge close to the nucleus where the positive charge is, which helps to stabilize it. Whereas if you draw the same orbital, the sp2 orbital on the other carbon, it's more elongated. So when the hydrogen leaves, the electrons in the bond go to form a lone pair on that carbon. Those would be in that sp2 orbital, and they would be further away from the nucleus, so they wouldn't feel the positive charge as much, and they wouldn't be as stabilized. And because it wouldn't be as stable, it would snatch back the hydrogen more often. The hydrogen wouldn't be able to get away. It would be less acidic. Okay. How about in this next one? Now we have a lot. It says identify the most acidic proton, and notice that they're using the word proton synonymously with hydrogen. Hydrogen is an atom with 1 proton in its nucleus. It's a proton with 1 electron going around it. So proton with 1 electron going around it. If you take the electron away in order to get that H+, then it's just a proton. So they're asking which proton is more likely to come off the molecule. And so what you'd want to recognize is the hybridization of each of these things. On anything that has all single bonds, it's sp3 hybridized. So these are all sp3, 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 all single bonds. Any carbon that's involved in a double bond will be sp2 hybridized. So that would be sp2, sp2. Because it has one pi bond, it's using a p orbital for that. It only has two p orbitals left to mix together. Anything involved in a triple bond is sp hybridized. It's making two pi bonds. That means it's using two p orbitals. It only has one left over to mix. So those are the hybridizations. And the rule for these, well, you'd really want to go through ARIO all over again. All the hydrogens are on carbon, so the atom doesn't help us. For resonance, you just have to worry about the allylic positions, because there are no positive charges here. But these allylic positions don't have any hydrogens on them. And so, because there are no hydrogens in allylic positions, there's no resonance in the molecule. So we'd go down to induction. And you'll notice that there are no electronegative elements here. No nitrogen, oxygen, fluorine, chlorine, bromine. So we don't have the negative charge that would be left behind being spread out through induction, stabilized through induction. So we finally get down to the last factor, and that's the orbital. And so we've drawn these orbitals on here, and our rule was that hydrogens on an sp hybridized carbon are more acidic than on an sp2 hybridized carbon, which is more acidic than on an sp3. We only have one hydrogen on an sp hybridized carbon. It's right here. Notice that this carbon already has 4 bonds, so there are no hydrogens there. And so that hydrogen is the most acidic in the whole molecule. All right, now we can do a similar procedure here. If you go through these 4 steps yet again, you'll see that all the hydrogens in this molecule are on carbon. So carbon doesn't help us. The atom doesn't help us. There are no allylic hydrogens here. So there are no hydrogens that would leave behind allylic lone pairs when they pop off the molecule, so resonance doesn't help us. There are no electronegative atoms nearby, near to any hydrogens that could help to spread the negative charge out through induction. So we're left with the orbitals. And so we'll just want to label the orbitals here. Any carbon that has all single bonds is sp3 hybridized. If a carbon has 2 pi bonds, then it is sp hybridized. So these 2 carbons are sp hybridized because it's using 2 p orbitals, one for each of the pi bonds. So it only has one left over to mix. So those are sp hybridized, and our rule was that any hydrogen on an sp hybridized carbon is more acidic than a hydrogen on an sp2, which is more acidic than a hydrogen on an sp3. And so this hydrogen is the most acidic because it is on an sp hybridized carbon. That's most acidic. sp3 is the least. Okay. Finally, we can do the same sort of procedure with this. Let's first consider the atom. All the hydrogens in this last molecule are on a carbon, so they all tie. The atom doesn't help us. We have 2 allylic positions, but those 2 carbons don't have any hydrogens on them. They already have 4 bonds drawn in. So there are no hydrogens that could pop off and leave an allylic lone pair, so we don't have any resonance. Induction, there are no electronegative atoms in the molecule that could help spread out a negative charge left behind by a hydrogen that left. And so there's no induction, so we're left with the orbital. So let's label the orbitals. Any carbon that has all single bonds is sp3 hybridized. Or I should say any carbon that has no pi bonds, that has no p orbitals. That's doesn't have any need for a p orbital. And then any carbon that has 1 pi bond is sp2 hybridized. Let me actually move these just a little bit. So this is sp2, and this is sp2. These carbons right here. There you have one. They're using 1 p orbital to make that pi bond, so they only have 2 left over to mix. So we saw that hydrogens in our little table, and we went through the explanation, we saw that hydrogens on an sp2 hybridized carbon are more acidic than hydrogens on an sp3 hybridized carbon. Notice we don't have any hydrogens on sp hybridized carbons here, so the most acidic ones will be the ones on an sp2 hybridized carbon, and both of those hydrogens will be equally acidic. They're in symmetrical environments. So, because sp2 hybridized carbons are in between, they're more acidic than sp3, which are the least acidic. So hydrogens on those will be the most acidic. So you get a sense of how you can look at the orbital on an atom and use that to assess the acidity of a hydrogen on that atom, qualitatively.